fluid flow analysis and simulation using PTC Creo. The given condition is water is flowing through a pipe having uniformly varying diameter from 30 centimeter to 15 centimeter. That means two diameter, one end is 30 centimeter, other end is 15 centimeter, and length 30 centimeter. If the inlet velocity of the water is 0.5 meter per second, we need to find the mass flow rate through the pipe and the pressure at each section. That means the variation in pressure throughout the section and the flow streamline. So go to PTC Creo. Let's create the tapered pipe. Control N. Let me name the file as pipe. Just check the unit, which is millimeter Newton second. So go to front plane and use a revolve tool to create that pipe. The condition is the diameter is 30 centimeter and 15 centimeter. Okay, so here the diameter is 30 centimeter, that means 300 millimeter. So the radius will be 150 millimeter, and here it is 150 millimeter diameter, so the radius is 75, and the length of the pipe is 30 centimeter, that means 300 millimeter. Just dimension that line 300 and create a center line to revolve. Click on OK. Now the part is completed, but it should be hollow one, so use the shell command. Go to shell and click the surface. We need to remove the other surface too, so click and hold the control button and select the other surface too. Now it is a hollow pipe, and we have the thickness. So I can give any thickness because I am analyzing the internal portion only, but you should care about that. The 5 millimeter thickness, now it is at the inside portion. That means the diameter is now reduced. So we need to flip the direction of thickness, right? That means the thickness is towards outside. So click on OK. Go to the default orientation. This is our pipe. For the finite element analysis of fluid, that means computational fluid dynamics, which is commonly used, go to applications. We have a simulation tab and a flow analysis module inside the application. Go to flow analysis. We have a bunch of tools. Now it is deactivated. We have a wizard, that means a step-by-step procedure to complete the analysis. That means the pre-processing stage, assigning the material, meshing, and the processing phase. That means the analyzing and post-processing phase. All this done through the wizard. Go to wizard. So now it is asking for the name of the project. It is pipe flow. Let's name it. Then click on next. We have a bunch of tools related to the fluid flow, and we are considering the flow, and maybe some turbulence will be there in our analysis. And multi-component mixing, we are not using a simple pipe flow itself. Radiation, no heat transfer is happening. Streamline, yes, we need to find the streamline of the flow. And translation, multi-phase, cavitation, heat, which is any of these modules we not using in this session. So go to next. And do we want to set gravity force? You can set the gravity by click on gravity and in what direction, the y direction 9.8 meter per second. So, but in this analysis, gravity have no role to control the flow of the water. So let it be in no. The next one, do we want to create the fluid domain? Fluid domain means which is the volume that our fluid will flow. So yes, we need to create the fluid domain. We have internal, external, and both. If you are dealing with any pipe flow, which is an internal fluid domain, and if you are dealing with uh, any aerodynamic structure, so it will be an external, and if it's an hybrid model, so the selection will be both. So in this case we have internal section, so click on internal. Now we can see the tab of openings. That means two surfaces are selected for opening. That means the first one is this one and the other one is uh, the smaller diameter, right, which is okay. So click on add to simulation. That means both the surfaces will be add to the simulation. Then click on okay, right. Now the module is completed. That means the fluid domain is created. We have two options, CAD bodies and flow analysis. The CAD body is actually activated. So let me click on CAD bodies. That means you can see the fluid domain only. And if you click on CAD bodies, now it is visible with CAD body and fluid domain. So again, click on next. Then the fluid domain is actually already defined. The material is, by default it is air, so drop down that material to search for water. Water is a fluid. Then click on next. And are there any inlet boundaries? Yes, as per the question the inlet conditions are given, so yes, click on yes. And we have two surfaces and a fluid domain is here, so click on any of the surface. Now it is highlighted. It is actually our outlet face. So again click on that surface and click on the other surface. Yes, this surface is our inlet, so click on that and go to next. So now we have to give the boundary condition of the inlet face. In our question, the inlet velocity is given as 0.5 meter per second. So check for the inlet velocity. Yes, specified velocity. And we have Cartesian, boundary normal and swirl. I can either go for Cartesian or boundary normal. Cartesian means in this our model it is along x-axis, but I can simply use boundary normal. That means normal to the boundary. That means the opening of that pipe. Normal velocity is given as meter per second itself, so 0.5 meter per second. And do you want to release streamline? Yes, I need to study about the streamline, so click on yes. Then next. Are there any outlet boundaries? Yes, I have outlet boundary. That means this face. So this boundary 0, 1 is the outlet. Now it is highlighted. Then click on next. Is there any boundary condition for outlet condition, outlet side? No, it is not given. So I can simply consider it as that flow is passing to the atmosphere. So I can select the pressure outlet, that means to the atmospheric pressure. Now I can give the magnitude of the pressure, which is in Pascal. Atmospheric pressure is 101,325 Pascal, as you know the value, 101,325. Then click on next. Then do you want to specify other surface to apply boundary condition? No, I have only single tapered pipe. Go to next. Do you want to set any volume parameters? No, I have already defined the volume. Then is it a steady state or a transient problem? And just take it as steady state. Then next, other one is the mesh generation. Let it be in default condition. You can set the maximum cell size or minimum cell size that we done in the structural analysis. You can play around with that, but just keep it in default settings. So it is ready to generate mesh. Click on OK. Then wait to generate the mesh. Yes. Now you can see that the mesh is generator, and they're asking, the wizard is asking about the output that you require. We have volume type of outputs, boundaries, and you can monitor a point in the system. That means you need to find the change in velocity on a point or change in pressure on a specific point. You can either go for that. We need to find the flow rate of the volume. So if we check the volumetric flux and the mass flux which is available in the boundaries, so I select boundaries. It is now selected. Then click on next. Select boundary for output parameter settings. That means let me select this face. That means I think not BC2, it is BC1. Yes. So I need to find the mass flow rate, and let me check the volume flow rate as well. Click on OK. Then boundary XY plot output parameters. So we need to find the mass flow rate. So create new plot. That means XY plot 1. It's a name of a graph, and the other one is volumetric flux. So you can either plot both the values on a same graph, or you can create new. Mass flux and volumetric flux is not possible to plot on a same graph. So let me create a new one, XY plot 2. That means the output of this analysis will be having two graphs. That's it. Then click on finish. Do you want to run simulation? Yes. Now the simulation is running. Simulation is completed. Okay. So in the right side, the scale is given, pressure. Minimum is our atmospheric pressure. That means at the exit, and the maximum is at the entry. We know that as per the Bernoulli's theorem, as the area of cross section decreases, the pressure will also decreases and the velocity will increase. You know that. So which is we can see over here, right? Also we can play around with these graphs. That means the pressure at each point is required. So right. So go to streamlines. The other question is show the flow streamline. Streamline, just click on that arrowhead and click on streamline. Now the handles is available. Line thickness, that means the flow streamline thickness is given. Then the animation time, that means if you need to show the flow, it should be a non-zero value. Now it is a non-zero value. Then it is in the model tab. Go to view. The streamline is not actually animating now because I didn't define any of the quantity to show the streamline. That means we need to check the give the variable. Select the variable. That means let me find the velocity 900 meter per second of flow, right? And now you can see that the streamline is passing from inlet to exit, and the direction of streamline is also given. The color is showing the velocity of the flow, right? The minimum is 0 in the scale and the maximum is 2.048 meter per second. Okay, let me show the values in the plot. Now you can see that each and every section having a varying value. Also in the model you can define the line thickness and animation time. That means if you increase the limit, you can see the length of the stream, right? Like this. Okay, and also you can change the thickness of the streamline as well, right? So the last one is find the mass flow rate through the pipes. Mass flow rate, we have already given the plot at the output setting. So go to XY plot panel here, XY plot panel. You have a residual plot. That means at the iteration from 0 to 50 iterations are given to analyze this flow, and it is a residual plot which is not significant for our study. Then go to XY plot 1, which will gives the mass flow rate. You can see that at the initial stage the analysis is happening, and after some time the mass flow rate kilogram per second is given, which is 35.212 kilogram per second. And in the second exploit plot, which is the volumetric flux, so mass flow rate as meter cube per second, discharge itself, which is 0.035 meter cube per second, right? Click on OK.